Hello. In this video I want to look at some examples that I didn't really get the chance to cover in class, at least not in full. So what we're looking at right now, these were in your notes, is just graph analysis for a full graph. We've talked about various things, how to determine if a graph represents a function, if it's continuous, how to find domain, range, and so forth. And I just want to take a look at a couple examples where we put all of this stuff together. So right here in this first example, the first question I am asked is this a function? Well, so the question then I have to answer is, does it pass the vertical line test? Vertical line test means that if I take a vertical line anywhere on this graph, will it intersect the graph more than once? You can think about that and just imagine it with your eyes. You can sweep your pencil across, but I can see that yes, this will indeed pass the vertical line test, which is no vertical line is going to intersect it more than once. So it is a function. The next question asks, is this graph continuous? For it to be continuous, that would mean that I can draw it without picking up my pencil. There are no breaks, gaps, anything like that, no open circles floating around in the middle, just one solid piece of graph, totally connected. This is indeed a continuous graph. If I took my pencil or my pen right here and I run it along, I can see how this could be drawn without picking up my pencil. So this is continuous, it is not discontinuous. For the record, most of what we deal with in this class we will expect to be continuous. Later on we will encounter some things that are naturally discontinuous, but again, that is much later. For my domain, so I'm going to start this off setting up my set notation. My domain is the set of x such that, and my range will be the set of y such that, is what that vertical bar means. Now I have to figure out what the actual restrictions are on my domain, which means I'm asking myself, how small does x get? How small does it get is how far to the left will it go? And how large does x get? That will be how far to the right does the graph go. Now, another important question as I ask this, is there anything missing in the middle? Generally, that's not going to be a big issue. That will, because we're going to mostly have continuous graphs, it will just be a question of how small and how large for the most part. So how small does x get? Well, right over here I see this arrow, which means that if I were to zoom out, I would see more points in this general area, more points to the left and below this graph. So if I'm going to the left, if I'm going to the left forever, that means x will eventually hit negative 10, negative 100, negative 10,000. So we say that it is bounded below by negative infinity. So negative infinity is my lower bound. Negative infinity is less than x, which is less than. I keep going along. Like I said, I have all of these values. The largest that x gets is very large. Over here I will go to I will find more points to the right and slightly below where I'm at right now, and further below eventually. So that would mean x is less than infinity. My domain is negative infinity to infinity. X is between negative infinity and infinity. In other words, x is just a real number is all this is really saying. My range. So for my range, again, I have to ask a similar question. How small do the y's get? How large do the y's get? When I'm asking myself how small the y's get, that's asking me how far down does this graph go, because this is where I will find smaller and smaller y's. I go from y being 0 to negative 1, negative 2, negative 3, and so on, further and further down. How far down will this go? Well, again, I see on both ends of this graph, both sides of this graph, this is indicating to me, these arrows are saying that there are more points down below where I'm currently looking. So if it's going down, and it's going down forever, again, that's a lower bound of negative infinity. So negative infinity is less than y, which is less than. How large does y get? Well, this function I can see very clearly it does not go any higher than 3. That's the highest y value I have, 3. It does not get even a little bit above that. So I'm bounded above by 3. But for all the points on this part of the function, y does equal 3. So I will not just say that y is less than 3, I will say that y is less than or equal to 3. Now, that's domain and range. Domain and range, incredibly important. We're going to be dealing with that throughout the entire year. Next, we want to divide our domain into increasing, decreasing, and constant intervals. So, when you're doing this, very important, use X and work from left to right. I can't stress that enough. You need to work from left to right. Sorry, that was a little bit out of frame. So, as I come in from the left, now ignore the arrow, that looks like it's telling you to go down. It's just saying there are more points over in this lower spot. As I come in from the left, my points are going up, up, up. I'm going up, which means I am increasing. So I'm increasing for small x's, that is when I'm below -8 and outside the frame. So as x goes from -infinity to -4, I am increasing. I am increasing for x from -infinity up to -4. Now notice I did not use an equal to for either of these, even at -4. At this point, I am not increasing, I am not decreasing, I'm not even constant. At this point, what my graph is doing is turning. So increasing and decreasing will never use any equal to's. Never. Alright, so I'm increasing from -infinity to -4 as x goes from -infinity to -4. Then I have this portion of the graph that is flat, horizontal. That means that my function there is constant. Now constant intervals are not something that naturally occur. It'll be something that I put in there by force. So it should be pretty obvious when it's in there. Right here it's flat. So this function is constant for x between -4 and right over here x is -1. Then from there on out I begin to decrease. So I'm decreasing, and it looks like this is going to decrease forever. So I decrease from when x is between -1 and anything really large. It's going to go decreasing forever, so decreases as x goes from -1 to infinity. Alright, so we've talked about whether or not it's a function, if it's continuous, its domain, its range, intervals of increase, decrease, and constancy. Next idea is intercepts. These should be relatively easy to find. You can generally just spot them right there on the graph. So for the x-intercepts are points where the graph hits the x-axis. I've got one right here. I've got one over here. This point is -5, 0. -5, 0. Over here, this is 4, 0. Whenever you're asked to find an intercept, remember, you are actually asked for an ordered pair, so please give your answer in the form of an ordered pair. For my y-intercept, that is the ordered pair where I am intersecting the y-axis, which is right here. Now that looks to be 0 for the x-coordinate, as y-intercept means that x is 0. And 1, 2 looks like about 2.5. So that's my y-intercept. Now this next idea that's going to come up, zeros. An x-intercept means roughly the same thing as a zero of a function or a solution of f of x equals 0 or a root of some expression. So x-intercept, zeros, roots, solutions all mean about the same thing. I will certainly get the information from the same place. The only difference is x-intercepts are ordered pairs, they're points. But zeros are just the x values. So for zeros, I'm going to write x equals, and then I'm just going to list these, -5 and 4. If I had more x-intercepts, I would continue listing numbers. But my zeros for this function are simply -5 and 4. Now the last bit, end behavior. The end behavior is asking you what's happening on the left and right sides of this function. So as x approaches infinity is what this says, and here this says as x approaches negative infinity. As x approaches infinity, positive infinity, this is the right side. As x approaches negative infinity, that is the left side of my graph. So on the right side of my graph, I can see, what am I doing? I'm going right and down. If I go right and down, as I go down, that means the y's are decreasing forever, so they are headed towards negative infinity. My left end, as x approaches negative infinity, so the left side, also, again, I have y's that are further and further below my graph, so that means that y there is approaching negative infinity. Be prepared, because you will be asked several times throughout the course to do graph analysis like this on some function that is given to you. All right, let's take a look at another example. All right, here we see another curve which looks like it is comprises several different parts. So again, let's look. Is it a function? Does it pass the vertical line test? Quick scan with your eyes will tell you that there is no place where I have to worry about a vertical line intersecting this twice. It is indeed a function. Is it continuous? I can see very easily that if you trace this over, if you drew this by hand, you could draw it without picking up your pencil, which means yes, it is continuous, it is not discontinuous. For my domain, the set of x such that, well again, since it's continuous, I know that it'll be the x's between two values. How small does x get is the first question I need to ask. Over here, this is saying I'll have more points to the left side and above. If I go to the left, again, that means negative infinity is my lower bound for x. If I go to the right, over here, so I've got all these points in between, I got to figure out the largest that x gets now for my domain. Well again, this is saying I will find more points to the right and above my graph. So to the right, x goes towards positive infinity. For my range, range is the set of y such that, again, it's a continuous graph, so I know that it'll be the y values will be between two different values. First thing I have to ask, how small does y get? Well, it looks like right here I have this nice little minimum point. This is a minimum. I can see the x value is -5, but what I want again is the y value. The y value here, how far down do I go, is -5. So I'm using that y value and saying my smallest y value is -5. -5 is less than or equal to y, which is less than, how large does y get? Well again, I can see by the arrows both sides are going to go up forever. So that means bounded above by infinity. Now, I have increasing, decreasing, and constant. I'm going to consider these all at once, and again, go from left to right. As I come in from the left, trace along with your finger with the tip of your pencil. As I come in from the left, I'm going down. I'm decreasing. So I'm decreasing for small values of x, as x goes from negative infinity until when? Well, this stops decreasing right here at this point. At this point, x is -5. So I'm decreasing from negative infinity to -5. Then what happens? Well, there I change over. I go from decreasing to increasing. And I increase for all x's between -5 and right here, -2. After I increase, I have this portion of the graph that is totally flat. It is constant. Y is the same value across this section of the graph. So my graph is constant for all x's between -2 and 3. What happens then? Because again, this graph does a lot of turning and twisting. After it is constant, I begin to go down again. I am decreasing as x goes from 3 until 5. When x equals 5, this function starts to turn again. Lastly, after that last section of decrease, I begin to increase, and it looks like I increase thereafter. So x is increasing for values between 5 and infinity. And I can just list these like this. I could write these as sets much the same way as I did with domain and range, but we don't really need to worry too much about that. I want the sets for domain and range, but here, focus on the inequalities. Next up, I need my x-intercepts, I need my y-intercepts, and then I will use that information to find zeros. My x-intercepts, it looks like I have 1, 2, 3 x-intercepts. It doesn't really matter what order you list these in. This one is pretty obviously 5, 0. That looks like it's exactly on 5. So I will go with that. These two are somewhere between two integer values. Right here, this appears to be negative 1, 2, 3, 4, 5. Maybe negative 5.5, 5.6, something like that. I'm going to say negative 5.6, 0. And again, you're approximating, so I have to accept a few answers in a small range. Right here, this last x-intercept. Well, this is negative 1, negative 2, negative 2.4, negative 2.3, something like that. Again, approximate as best you can. Do what makes sense to you. You shouldn't be too far off of what I would guess. There's a small window of reasonable answers. Now, y-intercept. Well, the y-intercept, that's much clearer. It's right up there. The y-intercept is 0, 3. Now I need my zeros. Well, again, zeros and x-intercepts are basically the same thing, except zeros are just the x coordinates. So my zeros are 5, approximately negative 5.6, and negative 2.4. Okay? Then I have end behavior. I'm asked what happens as x approaches infinity, which again is the right side, and what happens as x approaches negative infinity, which again is the left side. Now again, you need to be able to think about these things individually, but this graph is, we can see on both ends, these arrows are pointing up. So both ends are pointing up, which means on both, for both my end behaviors as x approaches infinity and as x approaches negative infinity, y is approaching positive infinity. All right. I'm going to go ahead and do the last one here. If you've been watching, I would strongly suggest that you pause and attempt this last problem that is here. So hopefully you've attempted this. If you have, good. I'm going to go through this a little bit faster because the hope is, again, that you've attempted this yourself. So right here, I am asked, is this a function? Well, I don't see anything here that would stop it from being a function. I would need some other piece of graph that interferes with this or has the same x coordinate as one of these other points. So yes, it is a function. Is it continuous? Well, it is continuous. Remember, continuous means that it can be drawn without picking up your pencil. So it stops over here, but that's fine. It's continuous because I can draw this by just plotting this open circle, making that curve, and then putting an arrow to end it. So yes, it is continuous. It is not discontinuous. For my domain, the smallest x value is negative 4. Since that's coming from an open circle, I know I don't need an equal to. The largest x value, again over here, I'll find more points above and to the right. So the largest x value is positive infinity. For my range, how small does y get? Well, I can see right down here. The smallest y value on this curve is at this point. This is my minimum point, and it's where y is negative 2. As I go up from there, I will get every other y value, including 0, y is not 0 right here, but it is 0 at this point and at this point. And I go up forever. Again, over here I'll find more points that are above the graph. So y is bounded above, it is less than infinity. Increasing, decreasing, constant. As I come in from the leftmost side that I have, I'm going up. I'm increasing as x goes from -4. I can't start below -4 because I have no function over here. I'm increasing as x goes from -4 to -1. Again, as x goes from -4 to -1. Then this section of the graph I am decreasing. I decrease as x goes from -1 until x reaches 2. At 2, well, I resume increasing. And I'm increasing as x goes from 2 to infinity. Just keep increasing is what looks to be happening. Now you notice here I don't have any sections that are flat. Again, it would be obvious if it was flat. It's not meant to be. Maybe that's flat or maybe it isn't. There's nothing, there are no constant sections here. So for constant, I'm simply going to write none. X-intercepts. Well, it looks like I have some points here I need to approximate. Right here, that appears to be 4.5. So my x-intercept is 4.50. I have another x-intercept right here. That looks to be maybe not 0.5, maybe 0.7 or 0.8. So I will say 0.70. Now, this is a little bit tricky. Over here, since this is an open circle, that means I don't actually reach that point, which means it cannot possibly count as another x-intercept. So be aware of that. This would not count as an x-intercept. For my y-intercept, it's right here. That looks like 0, and the coordinate for the y is 1.5. My zeros, these are simply the x values of the x-intercepts. X is equal to 4.5 and 0.7 or 0.7. Or again, you might have written 0.8 or something like that. And my end behavior. Well, this one's a little bit tricky. Now, mind you, I wouldn't do this on a quiz or test. But as x approaches infinity, where does y go? Well, as x approaches infinity, we already established this is the right-hand side. On the right-hand side, I can see that my graph is rising. I'll find more points that are to the right and above. So if I'm to the right and above, then that means that y is approaching infinity. The left end, you're asked about what happens as x approaches negative infinity. Well, here's the thing. Our domain only goes from -4 to infinity. I never get anywhere close to negative infinity, so I can't very well talk about what happens when x approaches negative infinity. X does not approach negative infinity, which means this end behavior does not exist. This is a none. Now you should understand that. I would like you to recognize that certainly. Would I put this on a quiz or test and ask you to write none? It's very unlikely. I hope this has helped. We will be doing, like I said, graph analysis throughout the year, so hopefully you will gain comfort and confidence with it real quick. Thanks for watching.